Some of our sponsors that are joining us. Mark is a scientific lead at Cambridge Quantum Computing with a BS in physics and mathematics from Duke and a PhD in theoretical physics from Columbia. Spent about 10 years researching superstring theory and cosmology and co-authored 40 technical articles. And he is also a founder of the science crowdfunding platform, Fiat Physica, and nonprofit science partnership fund, an adjunct faculty at Singularity University, and a director of Astronomers Without Borders. Today's topic that Mark is going to cover is quantum computing, the new technology in computing. And you can find and follow Mark on the various social media platforms, LinkedIn and Twitter being two. So thank you again, Mark. And for us, for our organization, you can also find us. There's different ways to collaborate. You can, of course, join, be a member, volunteer, partner, or sponsor. We have our nonprofit status now, so I'm excited for our nonprofit launch. We just recently launched. And you can find us, of course, on our website or join our closed LinkedIn group, which is called Women in Big Data Forum, Facebook group, Women in Big Data. Follow us on Twitter and LinkedIn, Instagram, and all the content that is created can also be found on our YouTube channel. So feel free to subscribe and take advantage. All righty, with that, I'm going to hand it over to Mark. Thanks again, Mark, and over to you. I'm going to stop sharing so you can start.
Thank you, Sushi.
And yeah, go ahead.
Thank you, Sushi. And let me set my slides up there. Can you see that there?
Yes.
So thank you again for hosting me. I'm really excited to be here and be telling you about quantum computing. It's really an amazing time to be doing this because quantum computing didn't even exist commercially about 7 years ago. And so it's really extraordinary in that we were able to talk about this now. And so in this presentation, I'd like to share some of the highlights and kind of what it is and where it's at and where it's going, because I think this will affect every one of you, either if you're directly in the tech field or just interested in the tech field. This is going to affect everyone in the next few years. And okay, so before I get into the details, I want to say just a few words about the company I work for, Cambridge Quantum Computing. We were established in 2014, which makes us one of the oldest quantum computing companies in the world, actually. And we have kind of an interesting origin story. Our founder and CEO, Ilyas Khan, was chairman of the Stephen Hawking Foundation. And Hawking told him in 2014 that quantum computing was going to be big. You should get into this business. And so it's really extraordinary that Stephen Hawking was indirectly responsible for the creation of our company. We now have about 130 people worldwide. Most of them are based in the UK. That's why we're called Cambridge. We're actually from the university there. But there are a few of us in the US. I happen to be in Portland, Oregon at the moment. And we also have an office in Tokyo. About 2/3 of our team are scientists, and many of them have PhDs. We develop quantum software, and so we don't actually build the computers themselves. This is why we have partnerships with many of the main providers. And so IBM and Google and Microsoft. If you could mute it until the very end for questions, that would be great. Thank you. And so this is why we partner with all of these quantum hardware platform providers. And we're especially close with IBM and Honeywell. They're investors in ours. We focus on every type of quantum software there is: machine learning, chemistry, cybersecurity, and compilers. So I won't be able to talk about everything today, but these are the types of things that I will be talking about, kind of quantum computing in general, and then different aspects of quantum computing. So this is actually considered to be the first computer, and it's funny that it's almost exactly 200 years old, by Charles Babbage in Cambridge. And even though it looks pretty old-fashioned by today's standards, all of the ingredients are there. There's input devices and output devices, and most importantly, the way that it stores and processes information is identical to how it's done today. in the sense that it's really just switches which are on or off, ones or zeros. And so even though we've come a long way, the computers today they look much nicer, they're easier to use, they're incredibly faster and so forth. It's actually identical in the way that it stores and processes information. It's just ones and zeros using transistors. And so quantum computing is actually the first leap beyond that, in that it's a completely different way of processing information. It doesn't use ones and zeros. Rather, it uses quantum bits, which can be ones and zeros at the same time. So these are some of the definitions that we use in quantum computing. So for example, a qubit is kind of the basic ingredient. It's analogous to a bit, and it actually stands for quantum bit. And it's a two-state system, if you're familiar with that. Entanglement is this idea that multiple qubits can have their value depend on the value of other qubits, and they don't even have to be nearby. They could actually be very far away and have their value depend on it. Superposition is this idea in quantum physics where something can be in two configurations at once, and that's absolutely essential for quantum computing because we're talking about systems which are both in the 1 and the 0 state, and that's really the root of where quantum computing speed up comes from. And then finally, quantum supremacy. And in quantum advantage, it's this idea that quantum computers can do things that classical computers never could do in any reasonable amount of time. And so I'll be telling you about why that is soon. So this is why people are so excited about quantum computing. It's because every time you have a qubit, you're representing two states at once. So as I mentioned, one qubit can represent a 1 and a 0 simultaneously. When you add a second qubit, you actually have 4 configurations. And so they're all simultaneous again. Adding a third qubit gives you 8, and so forth. So you see, every time you add 1 qubit, you're doubling the number of configurations that you have. So just 30 qubits gives you 1 billion configurations at once. And 300 qubits actually represents the amount of information stored in all the atoms in the universe. And the reason that's significant is because if you built a computer from the whole observable universe, that would be as powerful as a quantum computer with only 300. And so even in principle, you couldn't build a normal computer more powerful than that. And so this is why people are so excited, because quantum computers would be more powerful than anything we could possibly even hope to build using normal computers. And so it's not just that they're faster, they could solve problems that we never could have hoped to have solved before. So this is why we want to build quantum computers, because we can have very complex problems and analyze them in much more detail. And these are problems that never could have been solved with normal computers. They really do exist. This is not sci-fi fantasy buzzword lingo type stuff. This is real. They really do exist. There's several different approaches. So several different ways of building these qubits. One common approach is superconducting, and this is an approach used by a lot of the big giants. So for example, IBM and Google, and a startup based in Berkeley named Rigetti. Another approach is called the ion trap technology. And this is favored by Honeywell and IonQ and others. And then there's others like photonic and such. Each of these has advantages and disadvantages. So for example, superconducting quantum computers are very fast, and we know they work. We have about 50 to 100 qubits, which actually work using superconducting technology, but they're still kind of fragile. The qubits lose their quantum properties very easily, and you have to keep the machine in this giant cryogenic chamber near absolute zero. So it's these giant refrigerators, and you might have seen these chandeliers that you have to dangle in there. And so it's very expensive, and there's a lot of overhead. Ion trap machines, on the other hand, they're slower, but they're much more stable, and you don't have to have all this expensive refrigeration stuff. So they're orders of magnitude more stable and can last longer, but they're also slow to perform the operations. So there's a trade-off there. So if you were to ask me who's winning this race, I actually wouldn't be able to tell you. I would say it's sort of like a marathon after 1 mile. Groups are using different strategies and such, and so it's really difficult to say who's the winner. And there will probably be several winners. This is a chart of where it's at right now. And please note it's on a log scale on the vertical axis here. Many of you are probably familiar with Moore's law. And the idea is that classical computers have doubled in power every 18 months or so. And quantum computing is on a much faster trajectory than that. So this blue line here shows the progress just made by IBM. And the single metric being used is the quantum volume. So the quantum volume combines a lot of parameters like the number of qubits and the quality of the qubits and so forth into one number, which you can compare to others. And so you see that this blue line, we've doubled the quantum volume every 12 months or so. So that's even faster than Moore's law. That's doubling every 12 months, not every 18. Now, Honeywell, on the other hand, they only started a few years ago, at least publicly. They've been working on it for many years. They believe that they're on an even faster trajectory. They believe they can increase the quality of the qubits by a factor of 10 every year, and they believe they can keep this up for about 5 years. So that means in 5 years, we should expect to see quantum computers about 100,000 times more powerful than right now. And so that would be absolutely amazing. And then IonQ is that one yellow dot up there. A few months ago, they announced that they expect to soon have a quantum computer with a volume of 4 million. And obviously that's several years ahead of schedule. So we didn't expect this for several years. I only put an asterisk there because this is kind of a claim of what they expect, and it's still in beta testing and it hasn't been confirmed by outside groups. They're a fantastic group, so I don't have a reason to doubt it. It just hasn't been confirmed externally yet. And so regardless of the details, you can see that there's really extraordinary progress happening, and we expect to keep happening in the next few years. So what do you do with it? So there's a lot of different applications, and people are just now starting to think about what they could do with this. If there's one message I want to get across, it's that quantum computers aren't good at everything. You can't simply take your program running on a normal computer and then run it on a quantum computer and expect it to be 1,000,000 times faster. It doesn't work like that. The logic behind the programming is completely different. And so there's only specific applications that can take advantage of that. And we're just now starting to figure out what those applications are. Now, one of the first applications was chemistry. In fact, this was the very first one realized. It was about in 1982, a physicist named Richard Feynman realized that normal computers would never be able to efficiently solve chemistry problems, because as a molecule gets bigger, you have more and more electrons all interacting with each other. And so the number of interactions increases very rapidly. So trying to put this on a normal computer, it would just choke. You could only do the very smallest molecules. So chemistry is definitely going to be a big application. And within chemistry, the big applications are personalized medicine, like designing drugs specifically for an individual, and material science, like designing more energy efficient batteries and such. Then there's areas like industrial goods and IT. Obviously, the financial industry is very interested in this, and I'll be talking about this in more detail. And then finally, cybersecurity. With a lot of people, if they know one thing about quantum computing, it's that it has something to do with hacking. And so I'll be talking more about that at the end. So I'd first like to talk about quantum machine learning and AI and how quantum computing affects that. So there's a lot of machine learning and AI now. It's sort of this ubiquitous tool being used in all areas of technology. And there's all sorts of specializations that people use. Regardless of which specific model you're using, the one thing it has in common is that machine learning is based on probability. And remember that probability is a number between 0 and 1. And so that's it. Everything with machine learning is based on probability. Quantum machine learning, however, is actually based on something called an amplitude or a vector. And the reason this is different is because an amplitude or a vector you can think of as an arrow, and they're added in a funny way. You add the head of one to the tail of the other. And so you get a bigger arrow like that. And so you see the mathematics is much more sophisticated. You can start out with 2 vectors and they're not 0, but when you add them together, if they happen to be pointing in opposite directions, they cancel each other out. And so there's much more sophisticated decision-making going on. And we expect that quantum machine learning could pick up on patterns completely missed by normal machine learning. So it's not just that quantum machine learning is machine learning, but faster. It's completely different mathematically. So we're starting from scratch. When we design these algorithms, we really have to kind of figure out how to think like a quantum computer and how to do this machine learning. So one thing that's already being commonly explored is what's called Monte Carlo analysis. And some of you might have familiar with this. Monte Carlo is when there's some sort of uncertainty in a problem. and you model this as a random variable. And so you're trying to predict the future, taking into account this uncertainty. And an obvious application of this is the financial markets. You don't know what's going to happen, but you're trying to make some guess about what value something will be. And so, so this has been used for quite a while, actually. And so the way you do this is you actually just have a simulation where you try lots of different outcomes, and you look at all these simulations, and then they kind of converge around something, and you take that as your answer. So quantum Monte Carlo it achieves the same thing. It uses very different mathematics. It's actually quadratically faster in the sense that you only need to use the square root of the number of simulations to get the same accuracy. So if you have to run 1,000,000 simulations to get some sort of accuracy using a normal computer, you only have to run 1,000 simulations on a quantum computer to get the same level. And so that's why people are very excited about this. And we're working on this, and many other groups are working on this. This is kind of starting to emerge as one of the first financial applications of quantum computing. Another thing is optimization. And so this is often when you're trying to minimize or maximize something like your profit or your risk or something, subject to some constraints. And again, people believe that there's actually quite a bit of speed up from quantum computers for this type of thing, including arbitrage and your portfolios and such. And these are just a few of the headlines that I grabbed from last year. Banks are not just starting to get into quantum, they're actually setting up their own groups. So for example, Goldman Sachs last spring, they actually created their own quantum group. They have their own quantum computing experts there. And many other banks are working with quantum companies to develop this. And so I think the financial world is going to be one of the first users of this. They obviously have the money that they can invest in this to develop this. So, an example of this is the knapsack problem. This is a pretty common thing in machine learning. So this is when you have some finite capacity, like a knapsack, and you can only carry so much weight, and you have different items that you can put in the knapsack. And each of these items has a value, so you're trying to maximize the value subject to this constraint. And there is no efficient exact solution known. It's pretty simple if it's just 4 items like here, but if you had thousands of items, it's very difficult to figure this out. And people have developed approximations and heuristics, but it's considered a hard problem to solve exactly. And so this makes it ideal to try to tackle using quantum computing. So this is a version of what we did. We actually wrote a quantum version of this. And so on the left, this is a 5-qubit version. And you see that the horizontal axis represents all the possible outcomes, that is, whether you include that item in your knapsack or not. And the vertical axis represents the probability of getting that answer. A very important difference between quantum computing and normal computers is that you're not guaranteed to get the correct answer. Because of this quantum physics involved, it's not deterministic. There's actually uncertainty inherent in the problem. And so the best you could hope for is that you will likely get the correct answer. So in this case, you see that we have about a 72% chance of getting the correct answer. Because it's a small problem we can run on a normal computer. So we know what the correct solution is. So it's kind of reassuring that the quantum computer is aware of the correct solution and gives it most of the time, but you see that it's not guaranteed to be so. So you see that we sometimes have wrong answers there. And then we actually did that on a real 5-qubit quantum computer with IBM. Then we ran the same version on a 10-qubit simulator. So it's a lot more items now. There's a lot more ways that you can do this. And again, the quantum computer gives the correct solution about a little over half the time. And this actually represents the state of the art. No other group has done the knapsack problem as much as this. So the second thing that I thought I would mention here is just how different quantum computers are with compilation and such. And I'm saying this because I think maybe there are some people interested in wanting to program quantum computers. And so I just kind of wanted to briefly touch upon how you would actually do that. Because these quantum computers being built are very customized right now. It's not like there's an assembly line at Apple spitting them out and everyone knows Python and C and everything. So these quantum computers are very specialized. They cost a lot of money, and each one has their own programming language designed by that group. And so it's kind of a hassle trying to move one program to another. To accommodate this, we've developed our own quantum compiler, which we call Ticket. and it allows you to easily move from one to the other. So Ticket lets you write your code once, and there's simply one line indicating which quantum computer you want to execute that on. And Ticket knows all the details of that quantum computer. So if it were, say, IBM, it knows all the details of the qubits and the couplings and the coherence times, and all of the technical stuff is done for you on the back end. So then when you run your program, it finds the most efficient way to run it on that particular machine. If you then change your mind and you say, well, I want to run on Honeywell's machine instead, you simply change one line in the code, and Ticket will automatically reconfigure your program to best run on the Honeywell machine. So you don't need to think about anything at all. And so the names here are all of the platforms that it now supports. And so all the major platforms Ticket already supports. This is kind of an example of why it's so important to be using Ticket right now. You want to make the circuit as efficient as possible. Because the qubits are still kind of noisy, it's really important that you keep the circuit as short as possible and use as few operations as possible. And so the formal name for this is called NISQ, Noisy Intermediate Scale Quantum. And Ticket is ideally suited for this. And so this is an example of how you would actually use this in practice. These are some of the new features just released a few months ago in the latest version. And we'll actually have version 0.7 in a few weeks. And so please stay tuned for that. The good news is it's free. This is the GitHub repo. You're welcome to download it right now and start using it. We make it free and available to everyone. We very much welcome your feedback. If you're using it and you have some feature you'd like to see for some application, please let us know. We're very interested in how people use it and any features and issues. So I encourage you to download it. There's also the issue of where do you actually have a quantum computer to use? And it's not as simple as like this laptop in front of me. You can't simply start coding. There are simulators that you can easily do on your laptop, but actually running it on a real machine is difficult. And so IBM has a low-level machine, the 5 and the 16 qubit machines. They're available for free, and you can use them right now. You just log on the cloud, and you set up an account, and you can start using it. But you're, of course, sharing it with a lot of people. There's a queue because this is public. To use the more premium, high-end ones, it actually costs a bit of money. We're actually authorized to resell this. And so if this is something that you're interested in for your enterprise, I'd be glad to talk to you about that. So the third thing I wanted to mention is cybersecurity. And again, this is kind of the one thing that people know about with quantum computing. It has something to do with hacking and such. And so I'll explain why that is. So this is a picture showing why encryption works pretty well. It's not sent as is. Because the data might be sensitive, we usually send some sort of encrypted version. So we apply a complicated mathematical formula to the data, like your credit card numbers, and we send that encrypted version, and then the person on the other end has some key, so some sort of numbers which can undo the mathematical formula and recover the original data. And I know we hear stories about hacking and such, but this actually works pretty well most of the time. Usually when you hear about hacking, it's because there was some sort of human error. It's not because someone used a computer to undo the encryption, to undo the mathematical formula by brute force. So this was developed decades ago, these formulas, because these formulas were purposely made so difficult that a normal computer would not be able to undo them in any reasonable amount of time. You would need supercomputers running for hundreds of thousands of years. And of course, that's not really feasible, and it would cost a lot of money. So this is why most of the time encryption works pretty well. Unfortunately, they didn't know about quantum computers when this was developed. And it so happens that the formulas that they chose a few decades ago, they happen to be formulas that are very efficiently solved by quantum computers. And this was realized some time ago. About 25 years ago, this MIT professor figured this out. He actually was able to write down the recipe for how a quantum computer could undo some of these mathematical formulas. Now, 25 years ago, that wasn't such an issue because there were no quantum computers. And so it was kind of an academic curiosity that this could be done, but it wasn't taken as any sort of serious threat. But now, given the developments in the past few years, people are starting to think about this. And so the good news is that people have already started developing new formulas. They're called post-quantum encryption algorithms, which are not easily undone by a quantum computer. So the top half of the screen shows some of the common ones being used now, and this represents about 99% of online encryption. So that's how significant this problem is. About 99% of encryption right now is vulnerable to quantum computing. The bottom half of the screen shows some of the suggested post-quantum encryption algorithms. And right now, there's actually a contest going on right now. It's organized by NIST in Colorado, and they invited submissions several years ago. They wanted people to come up with their best formulas to do this. So there's been intense scrutiny. People have been doing their best to hack these and defeat these algorithms. And just last summer, they announced 7 finalists. So they started out with hundreds, and they now have 7 finalists, which they think might be feasible to actually use in practice. It's still very much work in development. So we expect in the next few years, people will know a little bit more, and there will probably be 1 or 2 winners. There's probably going to be at least one, because there's a trade-off. Like a formula might be more secure, but it might take longer, and that would be difficult, especially if it was like an Internet of Things and there's not much power and such. So this is very much work in progress. People are thinking about this right now. So that's the good news. People are already starting to work on it, but the other bad news is that upgrading takes time. It's not as simple as flipping a switch and there you go. Everything is post-quantum upgraded. It takes several years to upgrade large systems. For those of you like CIO types for large corporations, you know this can take months or years. There's a lot of legacy systems. It's very complicated, and so I wouldn't wait until you hear about the first quantum hack to do something about this. A lot of companies are starting to do this right now because they know it will take time, and they want to be prepared for when quantum computers will be powerful enough to do this. As for the time frame on that, I truly don't know. People have different estimates. Some people think it could be just a few years away, like 5 years away. Some think 10, some think 20. So there's a lot of opinions about there. But again, we encourage you to start now. Don't wait until it's too late. And this is especially true because there's rumors that hostile governments are archiving things on the internet. And so in a few years, when their quantum computers become powerful enough, they would be able to just kind of read everyone's mail then. So even though you have data now, it would still be valuable in a few years. So that's the message. Start upgrading now. This is an illustration of how quantum computing can actually be used for a completely new type of communication, which is completely unhackable. And this is really based on quantum physics. So let me explain how this works. So imagine you had a source of entangled particles. And remember that entanglement means you have two qubits which are in the same configuration. You don't know what it is, but whatever it is, they're in the same configuration. And these are independently measured by 2 devices. We'll call them Alice and Bob. Alice and Bob each measure along a different direction, and they don't tell each other what it is. Only at the end do they compare which direction they measured along, but they don't reveal the answer. So when Alice and Bob measure along the same direction, they should always get the same answer because of this entanglement. So this is a secret key known only to them. Now redo this story, but there's some sort of malicious eavesdropper. We call her Eve. So Eve takes one of the qubits, measures it, and then replaces it with a qubit in the same configuration. If this were a classical physics system, that's the perfect crime because you would never be able to detect that. Eve knows what the value is, but has replaced it. So Alice and Bob would never know that things are being intercepted. But because this is a quantum system, the entanglement has been broken. And so now when Alice and Bob do their measurements, even if they measure in the same direction, they're not guaranteed to get the same answer. They may, but they may not. And so now when Alice and Bob do their reconciliation, they look at which ones, the values, they will not necessarily get the same answer. And they see there's a large error rate. So they have evidence that someone has been eavesdropping or tampering. And so it's a mathematical check. You don't need to just trust that it's working. You actually have a mathematical way of doing this. So this whole type of technology using the entanglement and looking for discrepancies in the different values. This is called quantum key distribution. And there's actually networks being built right now to do this. So, so South Korea is the picture I'm showing here. There's actually a network which is already up and running for much of the country. China's doing it, Switzerland's doing it, in the New York area, the UK is doing it. The advantage is, of course, as I said, it's unhackable. Any sort of interception is immediately detected. The bad news is that it only works over short distances if you're using fiber optics, because it's very easy for these photons to kind of screw up their quantum state. This quantum entanglement is very fragile. And so after about 100 kilometers, it doesn't really work. There's ways around that. For example, you can use space, and there are already quantum satellites which are being developed. So we actually soon expect to have some sort of quantum internet where there's quantum data being communicated. So this is a completely new type of communication which uses quantum technology to keep it secure. So that's it for my prepared remarks. It's really amazing what quantum computing can do, but there's also some risks, such as the hacking I talked about, and people should be aware of that. We think that we could actually see a quantum advantage in about 2 to 3 years. A lot of people are intensely developing applications right now so that in a few years, when the hardware catches up, they'll be in a good position to take advantage of that. And if this is something that you think would be at all relevant to your work, please talk to someone now about like starting a proof of concept project and learning about quantum computing. So I mentioned if you'd ever like to download Ticket, it's available for use for free. Just go to the GitHub repo. If you'd like to talk about hardware access, I can discuss that. I'd also like to stress that we're hiring a lot. We actually just closed a Series B. We expect to greatly increase the number of openings, particularly in the United States. And so if you're interested in a job or even an internship over the summer, we'd be glad to talk to you about that. Just send me a note and I can connect you with our team. So thank you very much. And I'm happy to answer any questions that you might have.
Awesome. Thanks, Mark. That was great. Well, I got to learn a lot too. So, all right, there's a couple of questions that have come in, and Adam and Amber, feel free to chime in, but I can also read them. So Adam says, could we run a problem several times over for a high probability of a correct result?
Sorry, so run it many times to make sure that that is the correct result. Yes, that's exactly what you do. So like that graph I showed with the knapsack problem. So what you do is you run it a few times, and because there's this quadratic speedup, even running it a few times should still be faster than if you did it on a classical computer, and hopefully you should see if the same answer is the output many times, that's probably the correct answer.
Cool. And there's a follow-up question. Are you a FOSS, F-O-S-S? Does that?
I don't know what that means.
Adam, are you there? Do you want to chime in? Or we can move on to the next one. The next question is from Amber. There seems to be a rift between people who believe quadratic speedups will be enough to be worth it, and those who say that if the speedup is not exponential, there is likely a classical way to do it.
Yeah, that's an excellent question, Amber. Thank you. And there's no consensus on this. This is exactly an issue right now. So there's two kinds of speedups in quantum algorithms. So there's quadratic speedup, which is like I mentioned, if you run it 1,000 times on a quantum computer, you would need to run it 1,000,000 times on a classical computer, because 1,000 squared is 1,000,000. And even though that's impressive, there's fears that that may not be enough, because there's overhead in the quantum computer. You have to initialize the qubits and run it, and there's error correction. So I didn't even talk about this. Because the qubits are so fragile, there's ways that you can smear the information from one qubit among several qubits. And so it kind of adds a lot of overhead to things. And so people's fear is that quadratic may not be fast enough to actually run in practice. It's kind of an intellectual, clever trick to see that it can be done faster, but if you actually run it, there will be bottlenecks like the amount of time to convert classical data to quantum data and then back again, and things like that. So the other type of speed up is exponential, and that's quite a bit faster as n becomes large. There's no consensus. So some people fear that quadratic isn't good enough, and some think it's just fine and we can resolve this. So I don't know the answer either. I don't think anyone does, but you're right. There's definitely a rift in the field about this.
Cool. All right. The next one is, what's the difference between a quantum computer and a simulator?
Good. So a real quantum computer is one that actually uses these qubits, which are truly in a state of quantum superposition. And so that's where the magic of quantum computing happens, because you're looking at lots of configurations at once. You can always simulate this on a normal computer. You can kind of pretend to have these qubits, and it's really just a linear algebra problem that you're solving. You're looking for the eigensystem of this matrix and such. And so you can kind of pretend like you're doing this on a quantum computer. But you might say, well, if I can do it on a classical computer, why do I need a quantum computer? Doesn't that kind of defeat the whole purpose of doing this? The problem is that every time you add one qubit, you're doubling the number of configurations. So 10 qubits is 1,000 possibilities. 20 qubits is 1,000,000. 30 is 1,000,000,000, and so forth. And so a normal computer just can't process that many things simultaneously. Your laptop can handle about 30 qubits. So there's simulators which let you pretend you're using a quantum computer on your laptop up to about 30 qubits, which right now is more than good enough for most quantum applications. There are more powerful computers like servers which can simulate up to about 40. And you might say, well, if going from 30 to 40 doesn't sound so significant, why is that laptop to supercomputer? But remember, that's going from like 1 billion to 1 trillion. That's actually 3 zeros there. So that's why there's a big difference between 30 and 40. And so because quantum computers are very expensive right now, we often run software on simulators first while we're doing this and everything. We understand it won't be as fast as doing it on a normal computer, but they're very useful.
Great. Well, that was Yasmin, and she also says, great talk. So thank you.
Thank you.
And Adam, he responded to FOSS, which means free and open source. So it's open source.
Okay. I apologize for not knowing that. Not right now. It may be in the future as the number of hardware partners expands. We're looking for different ways of engaging, and there might be some open source things that we do. Right now, our team handles it, and it's not open.
Okay, thank you. Next question is from Emmanuel. Are there practical benefits in simulating computers to solve problems, or the use of real quantum hardware is mandatory? Sorry.
The use of quantum is mandatory, like as opposed to simulators?
Yes. Are there practical benefits to simulating computers to solve problems?
Well, so the practical benefit is that simulators are very useful for testing. We would never use a simulator to solve a problem because it can't do anything that a quantum computer couldn't do. But simulators are just very useful for testing cheaply before one actually goes to use the real quantum computer.
Cool. And Emmanuel, feel free to chime in if you have a follow-up to that. But all right. I think the next is Thanky. Apologies if I'm not pronouncing your name right, but for running an optimization problem multiple times, does the Ensemble prediction guarantee optimality of knapsack solution like deterministic optimization solvers?
Very good question. No, so no, it's not deterministic. That's why when you look at that graph and you see all the different possibilities of what the outcome could be, you see that most of the time we get the correct answer, but sometimes we get answers which are not correct. And that's really hard for us to understand from a classical computing point of view. With normal computers, they are deterministic. If you tell them to do something and you get an output, if you redo that, you'll get the same output 100% of the time, unless the computer is actually just broken. And with quantum computers, you can rerun the program and get a completely different answer. It's not that the computer's broken, it's just that that's the quantum uncertainty. A lot of things are probabilistic and non-deterministic. And so the output will just be different. And that's very hard for us to get used to. We're not used to thinking like that.
All right. Then there's a comment by Dr. Satyam who says, great talk, Dr. Mark. Happy to discuss QC in energy sector offline.
Great, thank you.
And yes, there will be a blog and video recording available in about a week. So I don't know who asked that question, but I just wanted to answer. And Adam, what if we want to exploit the software commercially?
Exploit the software commercially. Is this in reference to the ticket license?
My guess is, Adam, do you want to add more context to that question if you're there? But so Adam asked the open source question.
Yeah, I want to write ticket code for the simulations. So yes, that's fine. We have no enterprise license that we charge for right now. So feel free to download it and start using it. And if you can get the quantum application running and make it commercially feasible, that's fantastic.
Okay, great. Another question from Tao. What would be the short-term foreseeable impact on financial industry?
Good, yeah. So the financial industry completely changed, with all these quantitative algorithms. It's not done by people having hunches anymore, of course. It's algorithms which look for patterns and try to predict things and everything. And so it'll be more of that, but the algorithms will be more sophisticated and faster, and they'll be able to handle more amounts of parameters and such. And so, yeah, I think it will just continue to be more automated in the financial industry. I don't know if that's good or bad. I'm not, yeah, my background isn't in finance, but that is definitely what would happen.
All right, cool. Those are all the questions that came in through chat. But if folks want to chime in and ask any other questions, feel free. Okay, Karen, what would you say would be a target date for industries to be using quantum computing?
Good. So you can actually, we're starting to do that right now. In fact, funny enough, Cambridge Quantum has developed a quantum key generator, which uses that entanglement process to generate random numbers and therefore random keys in a way that you can prove that the numbers are random using that same entanglement check. And so this is actually exactly something that we're developing right now. So I'd be glad to talk with you more about that.
Okay, Vivek, can quantum computing impact blockchain or payment technology?
Good. Yeah. So this is one of the most popular questions that people ask me. Could I use a quantum computer to defeat blockchain or mine all the Bitcoins or something like that? And there was a research article done on exactly this point about 2 years ago. And what they found was there's two separate issues. The question of could I use a quantum computer to mine all the Bitcoin? The answer is no. And that's because the Bitcoin generating algorithm is not something that a quantum computer is good at. GPUs are good at it, which is why people have NVIDIA farms and such, but quantum computers are not good at it. So the answer is no. The other question is, could you use a quantum computer to break the cryptography on cryptocurrencies and blockchain and such? And the answer is yes. If they're using conventional encryption, which is vulnerable to quantum computing, and you had a powerful enough quantum computer, then it absolutely would be vulnerable. And so you could kind of rewrite who owned the Bitcoin or things. And so so that definitely is an issue. And cryptocurrencies and blockchain will have to be aware of this and upgrade their encryption.
Hey, Mark, to that point, this is Elena. Do you foresee any legal compliance concerns that may come and start slowing down potentially the progress or the rollout of the capabilities of quantum computing? Can you speak to that?
Yes. So this is, yeah, it's very interesting. There are starting to be legal and trade issues with this because of the close connection with cybersecurity and national defense. So in particular, China, for example, is spending a huge amount of money on this. And of course, the government and defense industries are very closely connected in China. And so like Alibaba and Huawei and stuff are very much developing this. And the US was a bit slow to get started on this. There are no rules. I'm not aware of any major rules on this yet. It's still sort of the Wild West, and people will have to be thinking about that. So for example, the question I just had about random number generation, there are questions now about, is it a like a defense secret for generating random numbers? And that seems a little funny, like, well, if they're just random numbers, how can you classify that if they're random by definition? But the way that you generate them using quantum physics, that's very important. And so there are starting to be these issues which have never come up before. So the answer is nothing certain has been fixed, but people are starting to think about it.
Got it.
Awesome. Another question from Emmanuel. I'm finishing my PhD in electronics, analog reconfigurable circuits testing. Wow, that sounds very smart. And I feel very attracted to quantum computing. What advice could you provide me to steer my career once I finish to this area? I think that would be a good question for a lot of people. So
yes, so good. I'm glad that you're interested in quantum computing, and we need smart young people who are just out of school to get into this. To kind of illustrate the demand, when I started at CQC 3.5 years ago, there were about 10 credible startups. We were one of about 10 real groups doing this, and now there's hundreds. I can't even keep up with them. And so there's going to be a lot of demand for this, and it's very technical, and they need specialized skills. And so it's an excellent thing to be getting into right now, because it's sort of like the Silicon Valley a few decades ago. You're getting in on the ground floor, and you'll be creating the groundwork for a lot of really exciting things. What would I recommend to how to get into that? I would learn about quantum startups and what's happening. There's an excellent blog called the Quantum Computing Report, which has the URL quantumcomputingreport.com, and it's business focused. It's not super technical, and it has all of the latest updates in the field. There's charts of like who the players are and the progress that they're doing and what technology they're using, and yeah, so it's a really good resource for kind of who's who and such. And I would just start emailing people, explaining your interest in looking for internships, or you're finishing your PhD, just asking about possibilities. And as I said, we have a lot of positions opening soon, so please check our website for postings. That's always being updated. Yes, quantum computing report right there. Thank you.
Yeah, Eliana just put it in the chat. Great. Thanks, Regina and Eliana. Mark, I have a question just out of curiosity. What's next for quantum computing, like Cambridge Quantum Computing? What does the next year look like? And how can we as a community like support you or do anything to?
Sure. So the next year for us is going to be very exciting. We just closed our Series B in December. And so we're going to be on a big hiring push, as I said. So we really want to add a lot of positions, especially in the US. We're now starting to see real commercialization. When I started about 3.5 years ago, we were about to do our first commercial project. And then we had like 2 the next year. And then this year we had several. And then this year we expect to have many commercial engagements. And so it's really exciting to see how quantum computing is being applied to real world problems. And the other thing is we're starting to see so many new hardware platforms. So like about a year ago, Amazon announced that they were offering a platform to feature other quantum computers. And then just a few weeks ago, Amazon announced, they kind of strongly implied they have plans to build their own. And so so we're starting to see all these different approaches by all these different groups. And as I said, it's kind of like a marathon. I don't know who the winner is going to be, but it's really interesting watching all these different players in the race use different strategies.
Cool, great. All right, any other questions? I see Helen put a link in the chat for another quantum computing event. So feel free to, we'll share it with our community as well, Helen. So,
Super, thank you.
any other questions, folks? Mark, any last parting thoughts, comments?
No, thank you again for hosting me. I really enjoyed being here, and please feel free to email me with any further questions or if you're interested in positions. I'm glad to connect you with our team.
Awesome. Thank you so much. And as I mentioned, we'll follow up with a blog and Mark's presentation that can be found, the video can be found on our YouTube channel and the blog on our website. So thank you again. Appreciate your time. Thanks, Mark, and thanks
Thank you, Suchi. Thank you, everyone.
for joining us. Take care.